Welcome back to Table Talks. In this video, we're going to look at Newton's second law and the applications. But if we can remind ourselves, Newton's second law stated that the rate of change of momentum is directly proportional to the applied force. Therefore, we say that the force is directly proportional to the rate of change of momentum. And we say that to remove this sign of proportionality, we bring in a constant. And since m is common, we had to pull it out. But we know that acceleration is equal to v minus u over t. Therefore, our force is equal to k ma. But what if the force is 1 Newton? If we use a force of 1 Newton, and acting on a mass of 1 kilogram, and then giving it an acceleration of 1 meter per second squared, this shows us that k is also 1, and this value of k is also got from experimental results, and this leads us to the definition of the Newton. We say the Newton is a force which gives a body of mass 1 kilogram and acceleration of 1 meter per second squared. That is what we said, and this is some of the things we looked at under Newton's laws. Now, let us look at what we shall call impulsive force and then impulse of a force. An impulse of a force. Now, what is impulsive force? An impulsive force is a great force that acts for a little time such that its effect on the position of a body tends to be neglected. So we can define impulsive force and say that impulsive force is a great force, that acts for a very short time, and its effect on the position of a body is neglected. So when we have a great force acting for a very little time, and the position of the body almost remains unchanged, then we say that that is an impulsive force. So this impulsive force, we are saying impulsive force is a great force that acts for a very short time. For a very short time, and its effect on the position of the body tends to be neglected. Now let's look at what we call impulse of a force. What is impulse of a force? Now, impulse of a force, this is the product of a force and the time for which it acts. This is the product. This is the product of a force and the time for which it acts. So impulse is denoted I, therefore I is equal to force times time, i.e. impulse is equal to Ft. Now, having known that is impulse, what are the units of impulse? The units of impulse here will be a Newton second. In the units of impulse will be what? Will be a Newton. Let me see whether yes, it is a product of force and the time for which it acts. In this case, the units will be a Newton force per second. But we are going to look at the relationship the relationship between impulse and momentum. Here we are going to look at the relationship between impulse and momentum. Now, from Newton's second law, we can still quote that from Newton's second law, we found out that force is equal to mv minus mu out of t. This is what we got. And cross multiplying by t, this shows me that ft is equal to mv minus mu. But we have just showed that ft is equal to impulse. Therefore, our impulse here is equal to change in momentum, because this is final momentum minus initial is equal to change in momentum. Okay? Impulse is equal to change in momentum. Now, what from here we can now get a comprehensive definition of impulse of a force. Now from here we can define impulse, that impulse is the product of a force and the time for which it acts, and it is equal to the change in momentum. It is equal to what? To the change in momentum. So that can also be a comprehensive definition of impulse. Then, now, if impulse is equal to change in momentum, and we know that the units of momentum are kilograms meter per second. So this also tells me, since impulse is equal to change in momentum, then it can also have the same units as momentum. Okay? It can also have the same units as momentum. Then again, about impulse, we said that impulse is force times time. If we have a scenario where the force is changing, okay? When the force is changing, we are going to say that when a force is changing, okay, then impulse can be calculated from the expression average force can be calculated from the expression average force times time, i.e. I is equal to F average times time. This can also be a formula for calculating impulse from here. So this is related to that, but here we are talking of it when the force is constant. But here, if the force is constantly changing, so to calculate the impulse of the body when the force is constantly changing, we use this expression where we are saying that impulse is the force, is average force times time. Now, away from this, we have looked at the relationship between impulse and momentum, and we have seen that impulse is equal to change in momentum, and we've come up with a comprehensive definition of impulse, and this definition was that impulse is the product of a force and the time for which it acts, and this product of force and the time for which it acts should be equal to the change in momentum. So now let's look at some examples or scenarios that are explained by Newton's second law. Okay, we are going to look at the scenarios. Scenario number 1, we are going to look at one of the things that are explained by Newton's second law, and there are very many, but we shall look at a few, and whenever you see something that is in line with that, then always come back to our expression for that we derived from Newton's second law, as we're going to see in this example. Now, one of the things that are explained by Newton's second law is that when people are playing cricket, you see, when this person is trying to hold or to catch the ball, they catch the ball in a way that they are pushing their hands backwards. Why do they push their hands backwards? They try to increase the time of contact. Now, when they increase the time of contact, it means that the net force that acts on them is also reduced in line with Newton's second law. Okay? Now, when we look at this expression where F is proportional to V, kV over that, when this time of impact is increased, when you stay with the ball, you first receive it and then you take your hands backwards, you reduce the force that is acting on you, simply because we are seeing that force is inversely proportional to time. So for that reason, that's the reason why they tend to throw their hands backwards following the ball, so that they reduce the force on impact and reducing on the chances of getting pain. Number 2, here we are saying in receiving a ball. In receiving a ball, it is being used. Now, 2, we look at the packaging of China ware. When I say China ware here, I am meaning breakables that are always exported from China. When these people are packing these China wares, they try to see that they put them in some kind of a straw or some kind of paper. Like when you go to buy those China wares from the shop, you will find things of almost this nature between those things. Now, why do they put these things in between these things? See? That during transportation, we know that these things may tend to collide with one another. Now, to reduce the effects or to prevent these wires from breaking, they make sure that there is a straw between these papers, these wires, such that the time of impact is increased. And if the time of impact is increased, it means that the resultant force is also the resultant force is reduced, and therefore possible damages are minimized. The possible damages are minimized in that scenario. Then, scenario number 2, we are going to look at cricket players. When these people are batting the ball, they tend to wait and make sure that the ball spends more time with the bat. Why? Now, from F is equal to mv mu out of t. If we cross multiply and we come up with such an expression, the more you delay the ball with the bat, it means you're making it to have more time with the force on impact. And now, if time is long, it means this force of impact, it means that the impulse is also going to be high, giving a huge change in momentum, and consequently, this ball is sent away with a great velocity. So all these scenarios are being explained by Newton's second law. The other one is we are looking at long jumpers. Long jumpers, the athletes, all those things. Now, when it happens, for the long jumpers, for example, when they are jumping towards landing, they tend to bend their knees. Why do they bend their knees? They are trying to increase the time of contact and impact. So now, from this expression again, the moment you increase the time of impact, it means that you are reducing the reactional force that should be acting on you, and that one helps in doing what? Reducing the pain on impact. The same reason, if someone is falling on a cemented floor and then another person falling on sand, the person who's falling on a cement floor feels a lot of pain or is even hurt. Why? When you fall on cement, you go directly to cement and the time of impact is so small